Okay, so now we're ready to talk about the binary search tree, which is a special kind of binary tree, which is especially good for holding, items in an ordered set. Okay, so what's a binary search tree? A binary search tree is what we get when we place additional rules on where we can place things in our tree. In fact, we can have trees for lots of different purposes. But now we're going to focus specifically on this idea of a binary search tree. And the rule we're going to enforce, and at first we'll just consider this for integers, though we could generalize it to anything with a sortable key. But let's just pretend we're dealing with integers for now. So the general rule is that when we place something in our tree, it has to obey a less than or equal relationship between the parent, the left child, and the right child. And what I mean by that is that if we look at this tree over here where I have B as the root and A is the left tree and C is the right tree, then what we're going to say is that everything in the left tree is less than or equal to B, and B is less than or equal to everything in the right subtree. And this also implies that everything in the left tree is less than or equal to everything in the right subtree. And it always has to obey these rules. Another way is looking at it is that a parent is greater than all the nodes in its left and less than or equal to all the nodes on its right. And it doesn't matter which subtree you pick out of a big tree, this relationship has to be true. It's true recursively for all the nodes within the binary search tree. Now let's take a look at some examples. This tree over here on the left is a legal BST, a legal binary search tree. And all I mean by legal is that all of its nodes adhere to this rule. So let's take a look at it. If I look at node 7, then 7 is greater than or equal to 6. And there's nothing on its right, so it trivially satisfies that case. 5 is less, 1 is less than or equal to 5, and 5 is greater than or equal to both 7, 5 is greater than or equal to 1, and 5 is less than or equal to 7 and 6. Likewise, 9 is bigger than everything down here on its left, and 9 is smaller than everything over here. Likewise, 15 is smaller than 16. So this tree is properly obeying all of our rules. And so just looking at it quickly, you just think of it as whatever's to the left is smaller than its parent, and whatever's to the right is bigger than its parent. Now that equals allows them to be the same value. If we would like, if we have a multi-set, then that would be okay. But if we just have a normal set with unique items, then that would never occur. Okay, coming back over here, this to the right, this is an illegal binary search tree. In other words, it's poorly formed and it's not allowed. The reason it's not allowed is that node 8, way down here in 9's right subtree is actually less than 9. And so that is not okay. 8's in the wrong place. 8 needs to be moved over here to the right side of 5. And so if we put 8 here, it would be perfectly fine. Okay, so that's the essence of a binary search tree. Now, given a binary search tree, we can search for an item by exploiting the ordering. Say, I want to figure out where 7 is in this tree. So I'm going to start at the root, and since 7 is less than 9, I know I have to go to the left. But since 7 is greater than 5, when I get to 5, I know I have to go to the right. And then I've found 7. And so I found 7 doing 2 comparisons. I didn't have to look at every node in the tree. I only had to look at the nodes on the path from the root to 7, knowing that the binary search tree ordering has to be obeyed on all of these nodes. Here's another example. Let's say I'm looking for 22 in the same tree. Well, since I start at the root, and since 22 is bigger than 9, I have to go to the right. And then 22 is bigger than 15, so I have to go to the right again. And then 22 is bigger than 16, so I have to go to the right again, only there's nothing down here. And since there's nothing down here, that tells me there's no value in my binary search tree that matches 22, because if there was, it would have to be the right child of 16 or in the right subtree of 16. And since there's no right subtree of 16, 22 isn't present. I didn't have to come over here and look at this other subtree because I know all those numbers have to be less than 9, and therefore 22 can't be there. Here's some pseudocode for how we might do this search operation. Right? This is very close to C++ code, but it's not meant to be exactly C++ code. Right? I've left off some semicolons and some other issues. So this BST search out pseudocode takes a tree as the first argument, and the data we're searching for is the second argument. And I'm assuming that inside this tree, there's a root that tells me what the beginning of the tree is. And so I get a value called node that's referring to the root. And then I'm going to have a loop that says, while that node is not null, while I haven't yet reached an empty subtree, right? This is a lot like a linked list traversal. While I haven't yet gotten to the end of the list, while I haven't yet gotten to the end of my tree, then compare the value in the current node with the data I'm looking for. So if that data matches, then I'm done. I found the data I want. So this is a case where I could find the data at the root of the tree. If my set is big and I have a lot of things in my tree, it's not likely you'll find it at the root, but it could happen. So you have to check, right? Could be at the root. Now, if it's not at the root, then I either need to go to the left or the right, right? So if the data I'm looking for is less than the data at this node, then that means I need to go to the left. So I advance my node pointer to go down the tree to the left side, down to the left subtree. Otherwise, the only other choice is to go to the right. And that's because the data must be greater than or equal. And so I'm going to go to the right and look for it there. And then this loop, after we advance the node, we loop back around. We make sure that we didn't advance to the end of the tree, right? We might have gotten a null pointer just then if we were at a leaf node. If the root was a leaf, we might have gotten a null pointer, or if we're somewhere deep in the tree and then we realize, oh, this node has no left or right subtree, then we would have to stop, and this while loop would let us stop, detect that we're null, and we would give up and return false that we didn't find the item. Otherwise, we keep diving down the tree, following whatever path we need to follow, right? Trying to figure out the exact spot in the tree where this node would exist if it's in the tree. And we're either going to find it, or we're going to get to the bottom, we're going to get to a null and realize it's not present. Now, how efficient is this binary search tree search? Well, let's assume there are n nodes in the tree, and that by putting the n nodes into a tree, the tree has a height of h, right? It doesn't really matter how we arrange the nodes in the tree right now. I'm just saying that, h is simply the height of the tree, whatever that height happens to be. And so here's what we know. We know that each comparison moves us down one level of the tree, right? As we search for a node, we're going to make a decision. And if we found the node, we stop. But if we didn't find the node, we have to keep going. Okay, in the worst case, the maximum number of comparisons we make will lead us to a node that's of the greatest height. Okay, by the time we get to the node of the greatest height, we're going to find out if our element is in the tree or not. And so what we can say is that search is O of H, is big O of H. In other words, we're bounded by the height of the tree and the number of operations we need to do. There's no way you can do more than the height of the tree. Because if you did more comparisons than the height of the tree, that would imply that the height was actually longer, right? And that would be the height of the tree. Now, a neat thing about this is if we assume our tree is perfectly filled out, that the last level of the tree is a complete level and fully filled out, then what that means is that there's this nice relationship between the height of the tree and the number of nodes in the tree. And in a full tree, in a complete tree, then if we have n nodes, then the height of the tree has to be log 2 of n. And that means that what we're really achieving is a logarithmic time complexity, where the number of steps taken to find something is equal to log 2 of n, where we have n things in the tree. Because the height of the tree has to equal log 2 of n. Now, if the binary tree is not filled, then that would not necessarily be true. Okay, so the most correct thing we can say is that search is big O of the height. But if okay, but um, if it is perfectly filled out, then it's logarithmic. So a binary search tree on its own doesn't really guarantee us this logarithmic time, but we are later going to see binary trees that do guarantee this logarithmic time. So a lot of times when people talk about trees, they just assume that a search is logarithmic. It's mostly correct. I'm going to prefer to call it big O of H, the same way the Zybook refers to it, but you should know in the back of your mind that if all goes well in the way we build these trees, they tend to be logarithmic in time. Okay, so in summary, a binary search tree is a kind of binary tree that enforces an ordering among all of the nodes. A parent node is greater than or equal to its left subtree and less than or equal to its right subtree. The ordering relationship among nodes enables efficient search, a big O of H, where H is the height of the tree. And the height of a tree is often as good as log n in height for n items in the tree. So this is quite efficient. It's not as efficient as a hash table, which achieves O of 1. It's a lot more efficient than a linked list, which is linear and is ON search. And so this is a nice point in between hash table search and linked list search.